Welcome to Dr. Sherry's Astronomy channel. The topic of this episode is a small clump of dark matter has been found near the solar system. Precise timing observations of pulsars show that there may be a small, invisible concentration of dark matter close to the Sun. Based on three primary lines of observational evidence, we believe the Big Bang occurred about 13.8 billion years ago. Those three are the Hubble-Lemaitre law, the abundances of light elements, and the cosmic microwave background. This was not only the beginning of space and time. It was also the birth of all the matter that makes up the universe we see today. At first, everything was concentrated into an extremely dense point. Then it expanded at an unimaginable speed. It became a vast cloud of gas, where matter was distributed almost uniformly. In its earliest moments, the universe was like a dense, hot fog that even light could not penetrate. As expansion and cooling continued, light was finally free to travel. This light, which we still observe today, is known as the cosmic microwave background radiation. At that stage, the universe was filled with gas that was nearly uniform. Even so, there were tiny fluctuations. Some regions were slightly denser, and others were slightly thinner than their surroundings. These tiny variations eventually grew into cosmic structures such as stars and galaxies. Today, we observe their growth as the large-scale structure of the universe. When we look at the nearby universe, galaxies are not spread out evenly. Instead, we see galaxy clusters, where galaxies are crowded together. We also see thread-like structures called filaments that connect these clusters. Dark matter plays a key role in this process of structure formation. Because dark matter does not emit, absorb, or reflect light, we cannot observe it directly. However, it exerts a gravitational pull. This gravity affects how surrounding matter moves and how it is distributed. In the early universe, ordinary matter interacted strongly with light. That prevented it from clumping together quickly. In contrast, dark matter hardly interacts with light at all. This allowed small density variations in dark matter to grow via gravity first. These became the gravitational seeds of cosmic structure. Those seeds then pulled in ordinary matter through their gravity. In other words, stars and galaxies did not simply appear. They gathered and grew along the gravitational scaffolding that dark matter formed first. In this sense, dark matter is the framework of cosmic structure formation. Gas falls into that framework, cools, and becomes dense enough for stars to be born. Stars then gather into galaxies. Galaxies assemble into galaxy clusters. To describe the nature of dark matter, scientists often use a model called cold dark matter. In this context, cold means that dark matter particles move slowly, rather than at relativistic speeds. Because they move slowly, they can be easily captured by gravity to form clumps. Under this assumption, cosmic structures develop from the bottom up. Small structures form first. Then they merge to create larger ones. In this growth process, dark matter first forms small, gravitationally bound clumps. These clumps then gather into larger systems. Eventually they build galaxy-scale and galaxy cluster-scale halos. Therefore, the massive dark matter concentrations we see today are thought to be built from many smaller clumps. The Milky Way is also believed to have grown into a giant galaxy through the merger of such smaller structures. So, did the universe really evolve through this kind of process? One way to test this is to find the small clumps that may still remain today. Even after billions of years of cosmic evolution and mergers, some small clumps may survive. A portion of a small clump absorbed into a larger one might persist as a subhalo. This means small remnants of dark matter could still exist in our neighborhood today. By studying the number, mass, and distribution of these remnants, we can test the fundamental properties of dark matter and the history of cosmic growth. Whether this cold dark matter scenario is correct has been tested through many different phenomena. One of the most important testing grounds is the Milky Way and its surrounding region. Measurements of stellar rotation speeds show that there is much more gravity in the Milky Way than visible stars and gas can explain. This strongly indicates the presence of a massive dark matter halo surrounding our galaxy. However, rotation curves only tell us about the overall strength of gravity and its average distribution. Is the halo smooth and uniform down to the finest detail? Or does it remain patchy, filled with many small subhalos? Rotation curves alone cannot answer these questions. That is why high-precision measurements using pulsars are drawing so much attention. A pulsar is a neutron star that rotates rapidly while emitting periodic signals, such as radio waves. These pulses are extremely stable. By measuring the arrival times of these signals over long periods, we can track incredibly tiny changes in motion. Because of this, pulsars are often called clocks in space. Using this precision, pulsars are now being used to search for everything from low-frequency gravitational waves to dark matter. The arrival time of a pulsar signal is not determined only by the distance between the pulsar and Earth. Gravitational effects along the path and the pulsar's own motion also play a part. If there is an invisible source of gravity near a pulsar, the pulsar is pulled slightly and undergoes acceleration. This acceleration appears as a subtle shift in the signal arrival times. In the case of binary pulsars, we can extract even more information. In these systems, the pulsar and its companion orbit each other. Their orbital period can be measured with extreme precision. The orbital period changes slightly due to effects like gravitational wave emission. We can also detect apparent changes caused by the system moving through the Milky Way's gravity. By calculating and subtracting these known effects, we can extract the specific acceleration along the line of sight. This tells us how much the pulsar is being pulled toward or away from Earth. If we assume the Milky Way's dark matter is smoothly distributed, we can predict what this acceleration should be. With this approach, a research team led by Dr. Sukanya Chakrabarti at the University of Alabama compared two things. They compared the accelerations inferred from multiple pulsar observations. They also compared the predictions from a smooth Milky Way model. If there is no local source of gravity, the differences should be minimal. However, if a local dark matter subhalo exists, several pulsars near each other will be pulled in the same direction. This creates a spatially aligned pattern in the data. The team used this alignment as a clue to estimate the most likely properties of the gravitational source. They found an extra pull that cannot be explained by a smooth dark matter distribution. They argue that this extra acceleration is most naturally explained if a dark matter subhalo exists relatively close to the solar system. So, how massive is this subhalo, and where is it located? The team summarized the most likely properties as a probability distribution, as shown in this figure. Darker regions and higher peaks indicate higher probability. First, regarding its mass, they obtained a value of approximately 10 million times the mass of the Sun. There is a range, from a few million to a few tens of millions of solar masses. Even so, it indicates a gravitational source far more massive than any individual star. As for its location, the distance from the Sun is about 1 kiloparsec. That is a few thousand light years. On a galactic scale, this is our immediate neighborhood. Still, as the figure shows, the uncertainties remain large. The mass and position have not yet been narrowed down to a single point. This is mainly because only 6 pulsars were used in this analysis. Even so, by using pulsars as precision clocks, we are beginning to probe the fine structure of dark matter that was once impossible to capture. As we identify more pulsars suitable for high-precision measurements, the distribution of dark matter subhalos will come into much sharper focus. I look forward to seeing what we discover next. Thank you for watching, and I'll see you in the next video. If you enjoyed this video, please don't forget to give it a thumbs up. Hit the subscribe button and the notification bell icon, so you'll be notified when new videos are released.